Right. Assalamualaikum warahmatullahi wabarakatuh. Good morning, team. We are gathered here as the consultant team for the new mixed-use township project. Before we dive into the technicalities, we need to understand the weight of this task. So we are designing a 11 kilovolt to a 400 or 230 volt distribution system. I would like to emphasize that this project is not just about wires. We also need to consider other factors such as ethics, professionalism, and legal compliance. So, any suggestions? How do you see this project?
So looking at the project context, we have a very specific mix, which is we have 300 residential units, 40 commercial lots, a school, and a healthcare clinic. The clinic is what worries me the most because in a medical environment, power continuity is a matter of life safety.
Exactly. Our technical scope is clear, but we must evaluate the distribution configuration like ring, radial, and interconnected power system distribution. And also we must uh, check the cabling option like the overhead and underground.
Okay, let's summarize the problem. We face on engineering dilemma. The municipal council wants a low-cost solution, but the stakeholder, the clinic and the business owner require high reliability if we go to the cheap. We fail the clinic if we go to expensive. We might lose the contract or burden the resident with high costs.
We also need to consider inclusive respect. This township will have persons with disabilities, or we call it PWDs, and also children. Our infrastructure cannot be an obstacle. If we put posts in the middle of the sidewalk, we are failing our social responsibility.
Legally, we must be airtight. We are bound by the Electricity Supply Act 1990 and the ESA Electricity Supply Application Handbook. So every decision today will must be defensible in terms of national standards.
Well, I see. Well, so our objective today was to define the boundaries. So what needs to be done? We need to provide a complete layout that steps down the voltage safely and also provides full reliability towards the residents. And we also, but what needs to be considered is that we have to consider cost, reliability, and how our project will impact everyone socially. So we have to take all of that into consideration. Well, great start, everyone. We have our scope. For the next session, we will dive into the configuration. Each of you will suggest and defend one system. I want each of you to suggest and defend one system. Let it be ring, radial, interconnected. And we also have to consider whether we want to use an aerial line system, or we want to use an underground system. We will hold a formal vote to see if we can all reach a consensus. So I guess we'll continue in the next session, right by the end of today. All right. So thank you, everyone. I will see you in the next session. All right, assalamu alaikum, everyone. So welcome back. So today is the technical battleground for this session. It is the technical battleground. So we have 5 systems to analyze. We have 3 distribution systems, ring radial and interconnected, and we have 2 electrical transmission systems, which is either aerial bundle cable or underground. So let's start the argument, shall we? I want to hear the opinion of everyone in this team. So who would like to start?
I'd like to start first. Okay, I'd like to
right.
officially open the floor by proposing the radial system as our primary configuration for the residential zones. Look, we have to be pragmatic here. We are working for a municipal council, not a private luxury developer. If we look at the engineering dilemma presented in our brief, our first major constraint is the budget. From a purely technical standpoint, the radial system is the most straightforward architecture we can implement. It involves a single path of power flowing from the 11 kilovolt to 400 volt substation directly to the load center. For the 300 residential houses, this is the industry standard in Malaysia. Why? Because the capital expenditure capex is significantly lower than any other system. We only need one set of switchgear, one main feeder cable, and we don't have to deal with complex protection coordination between multiple nodes. That's my option for the system.
Okay. I am firmly advocating for underground cabling as our primary method for the town center. From an ethical standpoint, it is the only choice that truly supports an inclusive township. By removing posts, we ensure that sidewalks remain clear for wheelchair users and those with limited mobility. Furthermore, we must consider the Malaysian context. Our infrastructure must be resilient against monsoon storms and lightning strikes. Underground cabling provides that protection, ensuring that the engineering dilemma of reliability versus cost is solved by choosing the most durable long-term option for the community.
So for my idea, I think I would recommend the ring main unit because think of the ring main as the continuous loop. It connects the supply back to itself, creating a 2 parallel path for electricity to reach the load. So, if one path fails, the electricity simply flow from the other direction. And the heart of the system is the ring main unit, or we can call it as RMU. So, with an RMU at our distribution point, we gain a total control. So let's say that if a fault happened in section A, the RMU allow us to isolate only the damaged section, and then we can flip the switches at the clinic, and the clinic is instantly fed from section B, and downtime is practically zero. So that's my recommendation or my idea.
I see. Okay. Any other suggestions?
Yes. My opinion, I would like to go with the interconnected system why I choose this system, because this is high level of the reliability. So if one primary substation fails, so the load is automatically transferred. So it's the best way to prevent any downtime for the school and clinic. So as we know, the interconnected system, power is flow like a web or a net. So electricity is still find the alternative path to reach the destination if the one line is a cut. So how does it work? So unlike a radio system where the single feeder supply a load, interconnected system link multiple generating source or primary substation together into the closed loop or mesh. So you can do a bi-directional flow, so the power can flow in either direction along the line. It's like a what we call that, the Riemann system. So, but it's depending on the demand and fault condition. So, so I see for the township layout, school clinic are considered the critical load, right? So, um, as we see the clinic, it has the medical equipment such as ventilator, refrigeration for vaccine and medicine. So those things require the what we call that, the N1 reliability. So the system can withstand the loss of the one major component without the system failure. Um, we can see that the radio system cannot guarantee this because it has the what we call it single flow, right? So, but an interconnected system can um for the school. So as we know, the school that has modern education relies heavily on the IT infrastructure. So maybe frequent outage disrupt functionality. So an interconnected system allows the utility to perform maintenance online without cutting the power to the school. So as they can simply benefit electricity from the other direction. Mm, yeah, I think that's all for the interconnected system.
Okay, I understand the concern about reliability, especially for the clinic and school, but we also need to be realistic and cost and practice practically. An interconnected system sound ideal on paper, but for small township of about 300 house, the investment required for advanced protection relay, communication link and coordination system is very high. So the system also increase maintenance, complexity and require skilled personnel, which may not be sustainable for the local council in the long run. That's why I propose using aerial bundle cable, or its main ABC, especially for residential area. ABC is significantly cheaper than underground cable because it avoid excavation and reinstallment costs, and installation is much faster. Okay, at the same time, it is safer than traditional brake conductor. Reduce the risk of illegal tapping at the perform reasonably well in Malaysian weather conditions. The approach allow us to control costs while still meeting safety standard, making the project financially viable without over-engineering the system. So that's all for me.
All right, thank you for all your suggestions. This is tough. Currently, from the way that I see it, we are currently in a dilemma between whether we want to be realistic and take into account cost, or whether we want to provide full reliability towards this township. I think we should hold a formal vote. So on one hand, we have option A, which I would like to call it the economy approach, where we use a radial distribution system using aerial bundle cables. Whereas we have option B, where I would like to call it the reliability approach, where we use a ring main distribution system using an underground transmission line system. So I would like to hold a vote. You all can raise your hands if you agree with this choice. So who would like to vote for the reliability approach? I see. So only 3 people. Okay, you can put your hands down. So as for the economy approach, I would like to vote for this one because, well, cost. Okay. You can put your hands down now. Well, the result is a tie. Well, we are stuck. If we can't decide, we can't really move forward with the project. On the other hand, we are worried about the clinics and about our delivery on reliability. Whereas on the other hand, we are worried about residential costs. What if we don't just pick one?
So you mean like a hybrid system or what?
Yes, exactly. So we can use an underground ring main system for the town center. Anywhere, all the areas in the township that are crucial for the townships, for the township's operation. For example, the town center where all the clinics, the schools, and all the commercial lots are there. So this ensures that they have N1 reliability. Then we can use an overhead ABC radial system for the 300 houses and all the other residential areas. What do you all think?
I think that actually works. It's a very pragmatic middle ground by proposing this hybrid model. We are essentially performing a strategic resources allocation, also allow us to concentrate the high cost, high reliability infrastructure, specifically the underground remain, exactly where the operational risk is highest, which is the town center. If we also look at the school and the healthcare clinic, these aren't just consumers. They are community pillars that require N1 contingency. An underground ring ensure that if one cable segment fails, power is rerouted instantly, which is vital for medical equipment and student safety. Meanwhile, by utilizing the overhead ABC radio system, for the 300 residential houses, we are significantly lowering the initial capex for municipal council. This isn't just about money saving, but it's about energy efficiency. We are providing premium reliability to critical zones while keeping the residential power supply within a standard, affordable budget that align with the NB guidelines. It effectively solve our engineering dilemma by proving that we don't need a one-size-fits-all approach to satisfy both the budget and our ethical duty of care.
And it is still protects the PWDs in the high traffic commercial zones by keeping those sidewalks clear.
All right. I think that the system might be a perfect choice. So does everyone agree on the hybrid system? Can you
Yes, I'm agree
Yes.
with the hybrid
I
system.
agree.
Yes.
It's
I
also
agree with
Yeah,
that.
I agree.
it's a
I agree.
strategic compromise compromised by keeping the high traffic commercial zones and the healthcare clinic on a underground ring main. We maintain inclusive respect where it's needed, most keeping public paths clear and ensuring medical service are not interrupted by weather-related faults on overhead lines.
I see. Okay, well, consensus reached. All right, for the next session, I think we can already focus on moving forward with the project. We will focus on the technical parameters of this project. I hope you all can do your research well, and if you have anything to ask, you may refer to me as well. All right, so we will continue in the next session next week. All right, thank you, everyone.
Thank you.
Okay, thank you, thank you.
Welcome.
All right, Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to the third session, everyone. All right, so I hope that this will be the last session and we can come to a full framework of our design for the electrical distribution and transmission framework design. Okay, for that. All right, so let's look at the numbers of our hybrid system. Adit, will you lead us through the analysis, please?
All right. Thank you, Alif. So now I will share with you our data. So give me a moment. So can you guys see the share screen?
Yes, I can see it clearly.
All right. So we will start with the estimated load. Now, as we can see, if every single light AC unit and a machine in this township were switch on simultaneously, our total load would be 250 kilowatt. So as you can see, the heavy hitters here 1,200 kilowatt coming from the 300 residential unit, and a significant 200 kilowatt dedicated strictly to the clinic. However, sizing our transformer for 250 kilowatt would be over engineering. It was capital and increase core losses. So per standard practice, we apply estimated estimated demand factor. So this brings us to the real number, which is the maximum demand. For the residential area, as you can see, we apply a factor of 0.6, assuming standard domestic diversity. And not everyone cooks and shower at the same time. So that bring the housing load down to 720 kilowatt. But if we look at the clinic, which I apply a much higher factor of 0.9, because in a medical facility, HVAC and diagnostic equipment run constantly. So we cannot gamble on diversity there. So when we sum this adjusted load, residential, commercial, school, and clinic, our total maximum demand stand at 1,401 kilowatt. So this is the baseline capacity we must guarantee today.
But we must look at beyond our immediate budget. It is easy to look at 200 megavolt ampere design and see an extra expenses. However, as steward of the public trust, we must view this through the lens of intergenerational equity. If we build for today's needs alone, we are effectively passing a massive financial and structural debt onto the next generation of residents. We must design for this capacity because of infrastructure should never be fragile. When a system operates at its limit, any small surge or minor heatwave can lead to a blackout. In an ethical framework, a blackout isn't just a technical failure. It's a disruption to life, a risk to those who rely on medical devices at home, and a blow to the local economy. By committing to the 2 mega VOMPS standard, we are building a foundation of resilience. Furthermore, we must consider the environmental cost of rework. Tearing up roads and replacing cable 5 years from now doubles the carbon footprint of the project and wastes ton of raw materials. Ethical engineering is about getting it right once. By calculating for that 30% growth now, we ensure that our current footprint is the only footprint we leave for foreseeable future. We aren't just calculating current, we are calculating the long-term sustainability of this township. In the end, our numbers, the 53 amps, the 11 kV, and the 2023 kVA are more than just data points. They represent our promise to this community. We must choose the path of foresight over the path of least resistance. Let's build a system that doesn't just work for now, but thrive for years to come. Because a township that can grow without fear of power failure is a township that can truly prosper.
Okay, so the transformer selection for the system, we selected 5 unit of 500 kilovolt transformer which and 11 kV to 423 volt, 400 and 230 volt rating, giving a total installed capacity of 2,500 kilovolt based on the calculated demand of 2023 kilovolt. The transformer operate at about 80% loading. This is a good operating point because it falls within the recommended economic loading range of 60% to 80%. Operating in this range ensure high efficiency, reduce thermal stress on the transformers, and still provide some spare capacity of emergency of all future load growth. Okay, for the technical perspective, the 400 kilovolt transformer size is commonly used in Malaysia urban distribution networks and is a standard size under TMB specification, making it easy to source and maintain. These transformers are most efficient when operating around 70% to 80% load, which match our system loading well. Using multiply medium-sized transformer instead of few large one also help reduce fault level, improve flexibility in load balancing between substitution, and makes maintain easier since individual unit can be replaced.
I'd like to elaborate more on why I strongly agree with the recommended 500 kilovolt ampere units instead of using a single 2 megavolt ampere or 2.5 megavolt ampere transformer. From a reliability standpoint, this is about risk mitigation and maintaining the N1 contingency we discussed in our early discussion. By decentralizing our capacity, we create a robust safety net. If one 500 kilovolt ampere unit goes down due to a primary fuse blow or an internal winding fault, we are unplugging the entire township into darkness. Instead, only 20% of the total load is affected because we are implementing a ring main system in the town center. We can quickly perform a switching operation at the ring main unit RMU to reroute power from an adjacent feeder, ensuring the school or the clinic doesn't stay offline for more than a few minutes. Furthermore, we have to look at this through the lens of life cycle cost (LCC) and operational efficiency. The 500 kilovolt ampere transformer is essentially the workhorse of Tenaga Nasional Berhad, which is TNB distribution network. It is a highly standardized size in Malaysia, which means spare parts like bushings, gaskets, and tap changes are readily available in local inventories. We won't be waiting weeks for a specialized technician or a custom ordered part for a larger, rarer unit. Additionally, by running 5 units, we can keep each transformer operating at roughly 80% to 81% of its rated capacity. This is the sweet spot for transformer efficiency. It minimizes copper losses and reduces thermal aging of the insulation, which effectively extend the lifespan of the equipment and save the municipal council significant money on the long-term replacement costs.
All right. For the safety and protection measure. So for the first one is a remain unit. So remain unit or RMU is a compact cell switchgear unit used in a power distribution network. So remain unit, they are equipped with a load break switch to safely turn off power under the normal load, and circuit breaker to trip automatically during a fault. So during refer to the network topology, or power can flow to the two direction. So if one cable fails, the remain unit can switch to the alternative supply, ensuring the continuity. So number two is a overcurrent and earth fault protection. So overcurrent is to protect against the short circuit or phase staging, or at SSA's load that make the cable. So, and the earth fault protection is to protect against the current leaking to the ground, as like maybe a loose wire touching the metal casing. So the overcurrent and earth fault protection, this is crucial because it's referred to the discrimination. If a fault occurs to the specific building, only that building breaker should trip, not the main substation breaker. So the relay are timed so the closest device to the fault trip first. Okay, so number three is a transformation protection. So high voltage fuse and low voltage breaker, they are primary defense if the transformers draw too much current due to an internal fault or massive downstream short circuit. This disconnected to prevent the explosion or the fire. the Bothoff relay. So this specific is to all immersed transformer. It has a gas actuated relay installed in the pipe between the main tank and the conservator. So the function for the relay or the brush hole relay. So if there is low internal fault, like installation burning, gas bubble rise, and trigger an alarm. So if there is a sudden massive short circuit, the surge of the oil trigger the relay to trip the transformer immediately. Other that is a low voltage protection. So first thing, the low voltage protection is a MCB, or we call it a miniature circuit breaker. So this thing is to protect the lower amperage circuit, like lighting and power socket. So this breaker is protect against the overload and the short circuit. Other that is a MCCB, so multi-case circuit breaker. Is similar to the MCB but built for much higher current. It often the breaker is seen at the main switch for the building. So for the other other protection is a RCCB or AICB, residual current breaker or earth leakage current breaker. So this thing is critical for the human safety. So it detects if the current is leaking, something like through a person touch a live wire, and it will cut the power instantly to the prevent electrocution. So the last of the protection is the SPD, surge protection device. So uh, this protection device is to protect a sensitive electronics such as like a computer, medical equipment. Is protect from the voltage spike caused by the lightning or grid switching. Um, okay, under that is a general safety system. So this ensures that if the live wire touch the metal enclosure, the current flow safely to the earth rather than through a person touching to the enclosure. So a low resistance path is required so the circuit breaker can detect the fault current and trip quickly. And lastly is a physical safety measure. So this is non-electrical barrier. So it's a lockable substation enclosure and restricted public access. So this thing is to prevent the unauthorized people from wandering into the dangerous high voltage areas. So warning signage is a legal requirement to alert personnel to specific hazard, something like the sign that show the high voltage or arc flash hazard. Okay, that's all for me on this.
Hello, Najon. I don't think we can hear you there.
Are you okay?
Hello?
All right, we can hear you.
All right. Okay, there
Okay.
you go. Okay, as you were saying regarding the ethical consideration.
Yes. Next, we go through to the ethical consideration. Okay, in our final assessment, we have fulfilled our duty of care. By choosing the underground ring for the clinic, we have secured life safety systems. Furthermore, by adhering to MSIEC 60364, we are preventing touch.
Sorry.
Excuse me, Najon. I think we have lost you again there.
Hello, can you guys hear me?
All right, yeah, we can hear you.
Okay, sorry for the technical issue. Okay, where are we?
Sorry, Najwan, we cannot hear you.
Hello? Okay. Okay, sorry for the miserable mic. Okay. I will start again. Okay, in our final assessment, we have fulfilled our duty of care. By choosing the underground ring of for the clinic, we have secured safety systems. Furthermore, by adhering to MSIEC 60364, we are preventing touch voltage hazards that could harm pedestrians during a fault. This design is not just about meeting the Electricity Supply Act 1990, it's about professional accountability. We have anticipated the hazards, followed recognized standards, and ensured that this township can function normally, keeping public confidence in our engineering institution intact. Okay. Uh, so the type of ethical consideration is avoidance of cost-driven negligence, selecting cheaper system with inadequate protection may reduce initial expenditure by increases long-term risk. Such this decision may increase accident probability, uh, cause preventable blackouts, and violate professional engineering standards. Okay, the second one is professional accountability. According to professional engineering codes, BEM, engineering must follow recognized standards, anticipate hazards, prevent harm through sound design. Okay, the third one, duty to protect public safety. Engineers have a moral and professional obligation to hold paramount the safety, health, and welfare of the public. The fourth one, responsibility to vulnerable users. This township serves elderly residents, children, patients in healthcare clinic, and also persons with disabilities. Okay, the last one is social trust in engineering systems. Public infrastructure must be trustworthy. Uh, when power systems are safe and reliable, communities function normally, business remain productive, and the last one, public confidence in engineering institution is maintained.
All right. After hearing all of your presentations, I can conclude that professionally we have followed the Electrical Supply Act 1990, and we are also we have also followed the TNB ESAH. So our design should be legally and socially responsible. So I guess to wrap it up, next week I will bring all of our findings um, towards our client basically, and we will have to present this. So I will need all of you to prepare a presentation slide regarding all of your findings. So every team member is required to prepare one slide or maybe two for the topics that we have discussed. So I will prepare the project context and objectives. Adib, I would like you to prepare the load estimation and maximum demand. Ashraf, I would like you to prepare the slide regarding the transformer selection and future growth. Miro, you will tackle on the safety and protection measures. And Shakarawi, I would like you to tackle the professional standards and legal compliance. And finally, Mr. Najwan, I would like you to prepare slides regarding the ethical considerations and the social impacts that our project will have. If this meeting goes as planned and the council approves of our project, we can begin. So I would like you to submit all of your findings in the form of presentation slides, probably by next week. So, okay, that's about it for this session. And I guess this is our final session. So meeting adjourned. Well done, team.
Noted with that.
Okay. Okay. Thank you.